Bismillahirrahmanirrahim. Welcome to Earthquake Seismology and Risk Assessment online class. And this is week number 11. And we are going to talk about seismic hazard analysis. As you know that we have discussed a lot of important concepts related to earthquake happening, earthquake physics, and we talked about the different causes of an earthquake. We talked about the elastic rebound theory. We talked about the theory of plate tectonics, and we talked about the strong earthquake ground motion, and we talked about different parameters of earthquake ground motion, and then we talked about the Fourier spectra and response spectra, and then single degree of freedom system, and other important concepts related to the earthquake physics and other components. So today we are going to talk about we also talked about the predictive relationships as well. So today we are going to talk about seismic hazard analysis. This is actually the application of the knowledge that we have already covered in the previous lectures. So how we are going to perform the seismic hazard analysis based on the known history of a particular area related to seismicity and tectonic setup, and the geologic evidence. Those are available over there to produce the similar type of seismicity in the future as well. So, so there are different steps to perform the seismic hazard analysis. The first and foremost important step is the identification and evaluation of earthquake sources. It means if you are going to perform the seismic hazard analysis of a particular, let's suppose, earth embankment dam. So that is a kind of mega structure. So first of all, what you need to do, you need to identify and evaluate the earthquake sources. It means first of all the recognition of the earthquake sources. What are the earthquake sources available in that particular area in terms of active faults, right? And then if you have identified the earthquake sources, then you need to evaluate the hazard that is associated to that particular area. So that is the important thing. So there are different indicators. Those can be used to find out to characterize the earthquake sources. First of all, the geologic evidence. So geologic evidence is based on the fault activity, what type of faults are available there, and the activity of those faults, how much faults are active, and then you need to know the magnitude indicators. It means what level of magnitude was associated with the particular events those were triggered in the past, and how we can expect the seismicity from those sources in the future. So this is actually called as identification and evaluation of earthquake sources, where geological evidence is the first step, and then we need to see the tectonic evidence. It means the tectonic setup of that particular area, and we will need to look for the tectonic evidence. Then historical seismicity, it means the written records related to the earthquakes, and instrumental seismicity, it means the recorded events. So instrumental seismicity is not old, it is of just 120 years or 10 years, so it's not more than that. So these are all the steps those are performed to identify and evaluate the earthquake sources. After having this kind of information of a particular area, then we can perform the deterministic seismic hazard analysis and probabilistic seismic hazard analysis. So these are the two techniques, those are very important, and these are site specific seismic hazard analysis. We will talk about these things in the I mean later on in this week. So first of all, we need to discuss the identification and evaluation of earthquake sources. We have just listed down these sources. And now we are going to talking about in little talking about these sources into the detail. So the geologic evidence. So if you are talking about the geologic evidence, then what comes in your mind? It means anything, and the most important thing is earthquake is a geologic event, right? So it means it is related to the some geologic activity that is taken place in the subsurface, and subsurface is also composed of rocks, and how the movement is taken place, that is because of the movement of the fault planes. So first of all, we need to see the surface expression of different features in a particular area. Like we need to recognize the fault scarps, shear zones, offset drainage patterns, and then we need to see the fault activity, what type of faults are available in a particular area, and what is their slip rate, what is the geometry of those faults, and then you need to know the volcanic activities. So all of the historic and prehistoric evidences related to the tectonic setup of a particular area we need to identify and evaluate. So here you see that this is the surface expression of the of a fault, and over here you need to understand how you can recognize the faults from the surface. So if you see here, you can check that this is a kind of straight line over here, and what kind of feature is over here. So we need to recognize that. If you carefully see this diagram, you can check that the it is we need to we can easily recognize the fault if you pay attention. Like this is a kind of drainage coming from this way, and you see that it should be extended over here, right? But it's not there, right? So this drainage is offset by a fault that has produced a displacement, right? You see here, over here there is a kind of 90-degree turn, 90-degree turn, and we have that drainage is moved over here. You see that? So it means this is a kind of displacement that has been taken place because of a fault. This is a fault line. So we need to recognize such kind of incidents by looking at the geologic evidences, right? In the other picture, you see that it is actually the aerial view of a train along the San Andreas Fault in Carrizo Plain, United States, and you see that this is a pretty much obvious rupture that was produced by the San Andreas Fault, and this is the longest fault available in US, and this is very active. So these are the geologic evidences. Similarly, you can also see the prehistoric evidences. And what you see over there, for example, over here, you can check that this is a kind of deposition that has a different type of layers. Like it has you can say it's sand deposits and sand deposit, and also some sort of other soils available. So we need to remember one thing: whenever there is a kind of deposition, according to the horizontal according to the law of horizontality, the deposition is taken place in horizontal layers. Like you can see the layers will be like that, and you can also see some of the bedding planes. If those are intact, there is no movement, so those will be originally in horizontal direction. The deposition. You can also experiment this kind of thing by mixing different type of soils in water and then let it settle down in container. You will see that, I mean, there will the deposition will be in layers, right? So here is a kind of soil profile. There is a deposition, and you can just see that there is a kind of eruption of some material. I mean, some of the material erupted this way. You see that the material is erupted this way. There was some kind of confinement, and then what happens? It goes up to this. It goes up to this, and then there is another deposition. You see that this is a kind of other deposition. And if you see the original bedding, you will see that these are kind of horizontal layers over here. You see that? But because of some other phenomena, what happens? uh, there was a kind of liquefaction that was happened in the past. This is all sandy soil, and then there was a kind of confining layer on that sandy soil, and then movement taken place, and what happens? Then that soil liquefied and it erupts in a kind of sand blows. These kind of activities are called as sand blows, right? So this is a typical phenomena that happened in the areas where there is sandy and saturated sandy deposits, and if there is a kind of vibrations, you can see that kind of sand blows in the form of volcanoes can erupt and deposit that sand in conical shape. So this kind of deposition was taken place in the past, and then there was a kind of uh, there is a kind of deposition, further deposition on that layer. So what is, and over here the sand particles are not in horizontal layers. They have randomly arranged, right? So they are randomly arranged. So it means this is not the original deposition. It is disturbed by some of the event. And how that liquefaction was taking place in the past, that is because of an earthquake, right? So this is a kind of evidence. This is a prehistoric geologic evidence, right, of a particular activity that was indirectly linked with the occurrence of an earthquake. So this is how these kind of activities can be identified in the field, but we really need a great experience so that we can understand such kind of evidences in the field and we can recognize those. So this is the tracing. You see that this diagram is actually the tracing of this profile, and you see here, I mean, how this dike was formed, and it broke this original sand layer and then deposited all of this sand in this form of sand blows because of the liquefaction. All right. So then we need to understand the fault activity, and if you are going to define the fault activity, then we need to characterize those faults related to with respect to the geometry. It means where is the location of that particular fault, and what is the length of that particular fault, and what is the dip angle, depth, and distance to the site. So these are the things those we need to define in order to characterize in order to characterization of the specific fault. Then we have seismic potential. So what kind of magnitude is associated? I mean, how big earthquake was triggered in the past related to that particular earthquake source. Then we need to see the styling of the fault. Styling of fault is related to the type of fault, like strike slip fault, dip slip fault, oblique slip fault. Dip slip में आपके पास normal faults आ जाएंगे और thrust faults आ जाएंगे. So these are the geologic evidence related to fault specific characterizations, right? All right. So In the previous lecture, we also talked about the use of faults for the seismic risk assessment. So based on that kind of study, different scientists have come up with the different type of relationships with the different geometrical attributes of the fault and the magnitude of an earthquake, right? So over here you see that there are number of recorded events and their equations based on the regression analysis. Regressional analysis can be done like that. We have earthquake magnitude and then many maybe earthquake length, and you can see such kind of relationship. We already talked about those relationships formulation in the previous lecture. So based on these kind of relationships, we have these are the equations, right? So first of all, what are the geometrical properties of the faults? The number one is length of rupture, then we have displacement, and then we have area of the fault. These are the three important parameters of fault geometry, those we need to know uh, in order to define the seismicity of a particular earthquake source, right? So over here, first of all, the seismologists they have the relationships for the rupture length. You see here, this is rupture length with the magnitude, moment magnitude, and for strike slip fault, there are 43 events, and the relationship is this, right? And if you are over here, you can find out the magnitude of a particular earthquake if you know the rupture length. Similarly, same equation can be written in an alternate way. So over here you have log of L is equal to 0.74 NW minus 3.55. So this is actually the alternate way to write this similar equation over here. Is it clear? And then this is for the rupture length. Then you have reverse fault. For reverse fault, you have 19 events, and this is the equation. And for and this is the alternate way of writing that equation. Similarly, for normal fault, you have 15 events. Okay, and you have then this is the equation, and these all three equations are for rupture length for different type of fault. And if you combining all these faults, and you can have a composite equation. You see that over here, the composite equation for all of these type of faults. If you count all these events and make a generalized equation, then this is the generalized equation, and this is the alternate way to write down. And this is the standard deviation of a particular relationship. Similarly, then again you have three type of faults, and then the relationship with the area of the fault. You see that this is the area, and then we have the equation, composite equation, that is including all of these three types for the area. And then we have again three type of faults like strike slip, reverse, normal, and then you have the relationship with the displacement. Uh, is it clear? And then you have composite relationship of magnitude with the displacement for all of those events. So this is how you can formulate the equations based on the recorded data. And here are the relationships. You see the graphical representation of the same equations over here, and magnitude with the surface rupture. These are the modern, you can say, the advanced relationships. In the previous lecture, we also talked about the basic relationships of these faults with the magnitude, and these relationships are the advanced versions. So we can use these relations in our to perform the seismic hazard analysis of a particular area, depending on in which area, which area your site is located. Similarly, you have a relationship with the rupture length, all three types, and then the composite relationship, and then you have with the displacements. All of these relationships indicating the direct relationship. It means if magnitude is greater, greater will be the area, greater will be the rupture length, and greater will be the displacement, right? So these are kind of direct relationships, but the trend lines are a little bit different. But the relationship is direct. All right. So this is a very important example. We need to understand how we are going to use those relationships to perform the seismic hazard analysis in particular area. So over here, you see that compute the probability that a moment magnitude means MW. So you just need to break down the components of the example. 7. Earthquake on San Andreas Fault. Fault is strike slip, right? Strike slip fault. So we already know this thing. Strike slip fault. All right. So San Andreas fault, we already know. I mean, this is the moment magnitude, that is 7.0. Would cause a surface rupture. Would cause means this is a kind of probability, would cause a surface rupture longer than 100 kilometers. Longer than 100 kilometers. So this is actually the question. Now if you go in the detail of that particular San Andreas fault, then you will see, then you will come up with the information that if you go to this section 2.4 point 2.2, then you will see that in table 4.1, the mean surface rupture for a magnitude 7.0 earthquake would be computed as this. I mean, how much rupture length will be produced using these relationship. If you strike slip, you can use this relationship. And first of all, you need to understand how much actual rupture length will be produced during with this magnitude earthquake. So if you put all the put the numbers like magnitude की value आपने यहाँ पे put कर देनी है और आपने L find out करना है. Then you will come up with that the rupture length of 42.7 kilometer will be produced if an earthquake of 7.0 is triggered along the San Andreas fault, right? But now you will think that in the example it is written 100 kilometer, the rupture length of 100 kilometer. It means here you are actually, that particular fault is producing 42.7 kilometer, but now we are going to predict what are the chances uh, for the 100-kilometer rupture length that will be produced by a 7 magnitude earthquake. But actually based on relation, this is 42.7. It means it is less likely that 7 magnitude earthquake will produce 100-kilometer rupture length, because actually it is producing 42.7. So it means this is a kind of probability. So to define the probability of particular events, you need to go to the section 7.2 of appendix C, and over here for the probability, first of all you need to find out the Z variance. Z variance, how you are going to find out the Z variance? The probability of rupture length that you are going to find, first write log 100 minus log of 42, that is the actual rupture length, and divided by 0.28. This is actually the standard deviation, right? So you need to this is actually the standard deviation, and this is the formula for Z variance already given in the appendix. So you will come up with this number 1.32, and then you need to see the table C. The probability that the surface rupture length would exceed 100 is 0.934. So this is the probability. How you are gonna get it? There is a kind of table. Over in that table you will see the values. I mean, you need to see, you need to check the where is written 1, and then you need to see where is 3, and against 3 you need to go to the second row, 1 and second the second number, and you will read out the number from here, from the table, like that, and then you will come up with this value, 0.0934. It means if you multiply it with 100, then the probability will be like 9.34. Definitely it will be having very low probability, because actually it is producing 42.7 kilometer. So what is the probability if it is computing the 100? It means it might have different probability, less probability. Now I am just asking you to compute the probability of the San Andreas fault that will produce the rupture length of 80 kilometer, right? How much? 80 kilometers. So this is actually the question for you. So you are supposed to answer me, by inboxing me your answer, how much will be the probability of San Andreas fault that will produce the uh, the rupture length of 80 kilometer, right? So this is your question, or you can say your little assignment to do and give me the answers. And same procedure you will follow, and you will be having same formula, and then you can come up with the number from this table. All right. So then we are talking about the geologic evidence, right? And in geologic evidence, we have talked about the fault activity, and then we have talked about the historical events, and then we talked about the magnitude indicators. And now we are going to talk about the tectonic evidence. Tectonic evidence is also very important. It means we need to know the tectonic setup of particular area, what type of tectonic boundaries are over there, and what is the activity of those tectonic boundaries. It means what is the slip rate, how annually those plates are moving, at what rate. So you see over here, this is the graphical this is actually the relationship that was established between the age of the plates and then the rate of convergence along those plates. And then the seismic events are also given listed at particular along the particular plates with the different rates of subduction, with different convergence rates. So these are all kind of converging plate boundaries, where there is a kind of convergence going on, and one plate is subducting underneath another heavier plate. So and then their age is given over here. So now you need to understand what. First of all, you see here is the rate of convergence: 2 centimeters per year, 4 centimeters per year, 6 centimeters, 8 centimeters, 10 and 12 centimeters per year. Himalayas have a kind of rate of 10 more than 10 centimeters per year, right? So over here that is also convergence, convergent plate boundary, but over here it is not written, but you can see that there are some other areas written over here. Those are the convergence going on over there. So first of all, you see there is a kind of trend line. This is the trend line, and over here you see 7.0 magnitude value earthquake, then 7.5, then 8. These are the trend lines, then the 9. So over here what you see, this is 8.5. Over here you see that the age in million, age in million is decreasing this way. Age in million is decreasing this way. Zero age mean over present. Current. The current year, or the current, you can say, the time in geological scale. So this is in millions of years. So the important thing is that uh, first of all, you see, if age of the plate is getting decreased, then the slip rate is getting, if the age is getting decreased, it means um, younger the plate, then more active it will be, right? So over here, this is the equation, and this is inversely proportional. And first of all, you see if the plate has one, let's suppose plate has 180 million years. So it means 180 million years, it means it is long ago, and it is more older. The first you need to understand that this is a kind of rate of convergence, and then the plate of the boundary, and then you see there are different type of events. Those are given over here. So this plate has a kind of 100 million years old, and then it comes to 180 million years, right? You see the events like triggered in the past along those plates, like 7.2 magnitude, and then you have this is the then you have Caribbean plate, then that is 7.5, and then you have the 8 magnitude in, you see that New Zealand earthquake, and Kermadec earthquake, Java earthquake. Similarly, you have kind of Sumatra earthquake that was triggered. I guess this is the little older earthquake in Sumatra again in 2004. The earthquake was again triggered that has, I guess, 8 point something magnitude, but this is little older earthquake. So similarly, you see Chile is on the top. Chile earthquake is the earthquake that was triggered in 1960, and this is the greatest earthquake ever recorded. It has the magnitude of 9.5. So this is the greatest ever recorded earthquake with this much great magnitude. No earthquake is triggered greater than that, right? So the important thing is that more is the slip rate, it means younger will be the plate. Over here, and the greater magnitude earthquake will trigger. You see over here, this plate has the age up to this much, right? And you see over here, this is very younger plate. So the younger plates have more seismic activity, and they have more slip rate. It means younger the plates, more is the seismicity. It means these are not very stable. Younger plates will not be having a stable kind of setup. It means these will be producing more earthquakes with greater magnitude, right? Similarly, if the age is little more over here, it means this kind of plates are little matured, right? It means these are little older, so they might have the earthquakes in the lower range. This is the lower range earthquake. Similarly, if the age is more over here, you see that about this trend line, then you have lesser magnitude values earthquakes. Then if the plate is getting more older, then we have a kind of less magnitude earthquakes. You see that the magnitude is less, the slip rate is less for the older plates. It means these are a kind of stable plates. So the chances of the earthquake happening is little low over there, and also the magnitude will also be of a low value as compared to the plates. Those are younger plates. This is the younger plate. This is again little older than that. So you see the major events are happening over here, and those have a kind of convergence rate greater than 10. Greater than 10 convergence rate have more seismic activity. So from this graph or relationship, we have a number of things to understand. Like if the age of the plate is more, it means plate will be stable and less earthquakes will be produced, and slip rate will also be less. If the plate is younger, it means there will be more, those plates will be more active, and more slip rate will be produced, and earthquakes will also be more, right? So for the older plates, because those are kind of stable plates, the rate of slip is very slow. It means the energy will be accumulated in a very slow manner, and the earthquakes will also not be of great value. So less damages will be produced in the areas where the plates are more older, and so it means those are kind of stable plates. So this is what we talked about, this subduction zone and the potential magnitude earthquakes with respect to their age and convergence rates. So please let me know if you have any question related to this graph. All right, so then we have historical and instrumental seismicity. Remember what we are talking about? We are actually talking about how we can characterize, how we can identify and evaluate. It means characterize the earthquake sources. So we are just talking about how we can define the earthquake sources and how we can evaluate them. So there are different steps we need to perform, and over here we are now discussing the historical and instrumental seismicity. Historical mean the written evidence of earthquakes, anecdotal and oral histories. Many great historians also write a lot of events like the natural calamities as well. So we can, if we read the old manuscripts, then you can see that, I mean, there are the evidences from where we can get an idea there was a kind of earthquake happening in the old areas as well, in the olden past as well. And we can guess that, I mean, how big those events would be if we know that, I mean, how many people were died, and what kind of scenario a historian is writing in their particular manuscripts about the history. So Chinese history is very old. I mean, they have like more than 2000 or 3000 before Christ history available. So we can, I mean, we can identify the different earthquake events in by reading those history manuscripts. So if you talk about the instrumental seismicity, it is maybe 100 to 120 years old. It means recorded history. So whatever is being recorded by the instrument is called as instrumental seismicity. Is it okay? So we can, but these are not, I mean, the instrumental seismicity is not pretty much, it means pretty much old, and there are hundreds of events, I mean, thousands of events, those were triggered in the past. So we can just guess those about those events by knowing the geologic evidences. But still, instrumental seismicity is continuously measuring the micro seismic events and also the mega seismic events happening every day around the world. And so we have plenty of instrumental data available to perform some sort of hazard analysis in any particular area. So there are online catalogs available where you can download the seismic data and perform your own hazard analysis related to a particular area. All right. So this is the you can say the seismicity map of Pakistan and adjacent areas. This is all based on the international catalog. There are international catalogs; those are available where the digital record is available about different earthquakes, and you can download that earthquake data with their coordinates, and then just lay down that data to the subcontinent and other part, so that, I mean, you can have a better understanding how the earthquakes are distributed in the different zones of your area, of your interest. So over here, it is the data is given in the form of the epicenter of different earthquakes, and with respect to the depth. You see that these are the different zones related to depth. You see that, I mean, there are shallow earthquakes, intermediate earthquakes, and deep earthquakes. So the most important or seismically active area is northern Pakistan, right? This is northern Pakistan, and then Azad Kashmir area is very active. And over here, you see the blue part. This is the Hindu Kush area. Some of the portion is in Pakistan, and Hindu Kush area is the most active area, and you can expect, I mean, a magnitude 5 or 6 earthquakes, I mean, every 1 month or 2 months or 3 months in that zone. And you also, I mean, see in the news, I mean, these kind of reporting is available. Few days ago, there was an earthquake of, I think, 5.5 magnitude in that particular area. So this is a very active area. And on the other, and also you see the southern part where the Balochistan and Quetta is lying. I mean, this area is also very active. You see a lot of shallow earthquakes over here as well. All right. So based on that kind of seismic activity, we can prepare our own seismic zones, and this is the kind of basic earthquake hazard map that was produced for Pakistan over here. This is based on the G value, and we already talked about G value. What is G value, right? This is actually is the ratio of the earthquake produced by the earthquake acceleration produced by the earthquake divided by the acceleration due to gravity, and the ratio is called the G value. So here you see that based on the G value, you know the northern area is all super active, and then Hindu Kush area, you know, over here is most active area, and some of the Kashmir area over here, and then you have Quetta region over here, you know, so this is also very active. And why these are active? Because there are number of fault zones are present in these areas. The Punjab or the Lahore area, Lahore and other districts are, a little bit safer or in safer zone. All right. So, and you know, in your next lab will be like that, talking about the tectonic setup, and you need to have this kind of map overlaid by the district map of your GIS file. You have already GIS files of Pakistan with the district map. You need to overlay that map on this by co-registering, and then you need to see that where your area is lying, and what type of seismicity is expected in your area, and how you are going to perform the seismic hazard analysis in that particular area. You need to talk about actually based on first of all you need to talk about the tectonic setup of Pakistan, and then you need to talk about the tectonic setup of the province where your city or district is lying, and then you need to talk about the tectonic setup of your particular area. How far is that particular area from a particular fault or any kind of seismic source? So in this way, you are supposed to write a kind of report of 2 to 3 pages about your area. You need to prepare a location map of your area by using GIS and remote sensing skills, and then you need to highlight your area on that particular map. And this is how you are going to perform. Your lab and giving a kind of report representing the seismic activity of your particular area. You can also lay down the tectonic map on your particular on Pakistan map, tectonic map on Pakistan map, and then you can lay down your district map over it, and then you can define what type of faults are available over there, and how you can define the seismic activity of your particular area based on those particular earthquake sources. All right. So this is what we talked about related to the earthquake source identification and evaluation. So this is the first step to perform the seismic hazard analysis. So how you are going to perform the seismic hazard analysis now? If you have all kind of information about the seismic source of a particular area where you are going to perform the seismic hazard analysis for a mega project like dam or a bridge or other kind of nuclear repository or other kind of structure that is very sensitive. So you have now, if you have all kind of background of the geologic evidences, instrumental seismicity, prehistoric seismicity, and tectonic setup of the area, based on that information, now you can perform the deterministic seismic hazard analysis, probabilistic seismic hazard analysis, you know, and there is other kind of hazard analysis approach that is called as published codes and standards. We will talk about these things uh, in the related to published codes maybe in upcoming lectures, but today we are going to, in the second part, we are going to talk about the deterministic seismic hazard analysis. That is a really important four-step procedure, and the step one is like the similar to the discussion we have already made just few slides ago about the evaluation and identification of the earthquake source. So this is the first step. In any area where you are going to perform the seismic hazard analysis, we have four-step procedure for the deterministic seismic hazard analysis that is called a DSHA. So first of all, what you are going to do, you are going to identify the earthquake sources. For example, this is your site, and you define that this is the earthquake source 1 and it has a kind of rupture length, any rupture length, right? So this is actually the identification. First of all, you need to identify this is an earthquake source over here, and then you have an earthquake source 3 over here, and then you have earthquake source over here. That is a kind of a three-dimensional earthquake source that might have, that is a kind of zone. It is not linear source, right? So this is a kind of zone, but these two are the linear sources. And now you need to characterize. Characterize mean what is the magnitude that was maximum associated magnitude or the seismicity. Magnitude indicator you need to define. How many earthquakes were triggered in the past, and what was the maximum value of an earthquake that was triggered over there, right? So these kind of things you need to perform at first step. First step is what? Identification of all the earthquake sources. Maybe there will be two sources, maybe there will be three sources, maybe one source, maybe there will be five sources, right? So you need to identify how many earthquake sources are over there. Those sources can impact. It's not like that. I mean, you are in Punjab and now you are talking about northern area and you say that you have five earthquake sources close to your site. No, because if you are in Lahore, I mean, those sources are not gonna impact your site. So, I mean, in such a way that it can produce hazards, right? So, you need to identify the sources, those can impact your site, right? So you need to characterize the sources, and then you need to define the maximum event, right? Identify mean, okay, these are the earthquake sources. Then you need to identify what is the geometry of that source. I mean, length, rupture length, displacement, area, and then you need to define what type of fault is that? Strike slip, dip slip, or the oblique slip fault. Then you need to define maximum event. How much was the maximum magnitude earthquake that was triggered along these faults? Every source will be having a different magnitude earthquake that was triggered in the past, having a range of magnitude actually. Maybe 10 earthquakes were triggered along that particular source, and maybe 8, maybe hundreds. So it depends upon the known seismicity of that particular area. So this is the step number 1. Similarly, you have step number 2. So the step number 2 is actually to first of all define what kind of ground motion parameter you are going to determine to define the seismic hazard. Generally, we take acceleration P G A. What does it mean? Peak ground acceleration. So it may be of PHA, peak horizontal acceleration, and peak vertical acceleration, right? Depending upon the earthquake source and nature of the movement over there. So then you have, this is velocity, and you can have angular velocity. I mean, you can have like displacement, all kind of parameters are available. We already know these parameters, but most commonly peak ground acceleration is used for the deterministic seismic hazard analysis, right? Then you need to select the appropriate correlation. Correlation means the predictive relationship. Predictive relationship, those we just talked about in the previous lecture, and also we talked about over here in the table 4.1, where the relationships are given with the magnitude of an earthquake and fault, right? Those kind of relationship, and also the other relationship, those are we discussed in the previous lecture related to at what distance what will be the ground motion produced for a particular event. So we need to select the predictive relationship. If we have, let's suppose, specific area and we have a kind of predictive relationship available for that particular area, then we need to mention what type of predictive relationship we are going to use. If you don't have any predictive relationship available for your area, then you need to take some global predictive relationships, right? So read out the chapter 3 where the predictive relationships are given. So we need to select what predictive relationship we are going to choose based on the known history of your area where you are going to perform the seismic hazard analysis, right? Then you need to select the appropriate site to source distance. Site to source distance need to be defined. It means we in the previous lecture we also talked about there will be different site to source distance scenarios available. So we need to define what type of scenario we are going to take, right? So generally what we do, we take the shortest distance. So this is a kind of shortest distance. That is actually the perpendicular distance from any source to the earthquake, any source to the site. So we take, for the simplicity, we take the shortest distance, but we can also take the focal distance as well or other kind of distance. But for deterministic seismic hazard analysis, we take the shortest distance. So this is the step number 2, right? स्टेप नंबर 2 में क्या है आपके पास पीजीए आप लेट्स सपोज आपने select the ground motion parameter, select the appropriate correlation, it means the predictive relationship, right? Predictive relationship, and then the appropriate site to source distance. तो डिस्टेंस जो है वो आप जनरली एपिसेंट्रल डिस्टेंस जो है ना वो लेते हैं, या आप शॉर्टेस्ट डिस्टेंस को ले सकते हैं, या आप फोकल डिस्टेंस ले सकते हैं, लेकिन जनरली शॉर्टेस्ट डिस्टेंस आप लेते हैं, ठीक है? Is it clear? So this is the second step, and there are total 4 steps. ठीक है, तो अभी मैं इसी जगह पे इसको स्टॉप कर रहा हूँ लेक्चर को. दिस इज द लेक्चर ए ऑफ योर वीक 11, आई मीन वीक 11 lectures. So लेक्चर बी विल बी अपलोडेड वेरी सून. और यहाँ तक जो है अगर कोई आपके पास कोई क्वेश्चन हो, कोई भी मसला हो, तो यू आर वेरी वेलकम टू आस्क. So thank you very much, and very I mean in a short period of time also I'm going to upload the lecture B, that is actually the continuity of this lecture. Thank you.